All right, so this should be a very short video, just reviewing and generalizing exponent laws that you've worked with over the last few courses and generalizing them algebraically here. And hopefully all of this sounds familiar. And so recall, if you are multiplying two powers of the same base, if you want, you can write it as a single power where you just add the exponents together. And that's probably something you learned in grade 8 or 9. And again, one thing you want to remember is that this goes two ways. If that's true, this must also be true, which means if you have a power to some exponent, you can break it up into two separate. So for example, if I have x to the 7, if I want, I could write that as x to the, I don't know, not 7, x to the 5 plus 2, which means if I look at this backwards, this must be the same as x to the power of 5 times x to the power of 2. And again, usually we tend to look at these exponent laws this way, but if they're true, they must work both ways. Okay, and again, I'm hoping this all sounds familiar. Looking at this, if we're dividing powers of the same base, you can write it with a single power in which you're subtracting your exponents. So x to the power of a minus b. And again, it can work both ways. If I want, I can take a power. If I write it as a subtraction statement, I can then write it as a division statement. Okay. As well, probably from grade 8 or 9, if I have a power raised to another power, I can write this as a single power. So x to the power of a times b. And so for example, if I have, again, x, or not even x, I don't know, 6 to the power of 3, and that's all to the power of 4. That's the same as 6 to the power of 12. And again, these are all things that go back several grades, but really, really important going forwards. So let's look at the next row. Here I have multiple factors, x times y, or two different factors being multiplied to each other, all being raised to a common power. If I want, I can write each of those factors individually to that power. So that's always true. And again, vice versa. If I have different bases being raised to the same power, I can write it all to that single power. So for example, if I have 5 to the power of 3 times 8 to the power of 3, if I want, I can write that as 5 times 8 all to the power of 3, or 40 to the power of 3. Again, the key is not that one of these is inherently better than the others, just they're all equivalent. All right. Dividing factors all to a common power, however you want to say it. Again, like before, I can write this as x to the a over y to the a. And I will say for both of these last two, quite often we show this visually as something like this or like this. However, and while I do that myself, we want to be clear, I'm not distributing the a. It's not like we're distributing a variable. It's not like we're going 2 times x plus 3 and we're distributing the 2. We're just basically using these exponent laws, but writing everything to that power. All right, what about a power of 0? Well, essentially a power of 0 you can think of as meaning something divided by itself. So x to the power of 0 you can think of as meaning x divided by itself, which is going to equal 1. And it doesn't matter what x is, anything divided by itself will equal 1, as long as that x does not equal 0. Because then you have 0 divided by 0. And remember, division by 0 doesn't make any sense. So as long as we have a base that's not 0 being raised to the power of 0, it'll always equal 1. I'm sure you can guess a common mistake, which I encourage you to write down. A common mistake is 0. And I understand why. But if you saw, again, 5 or 15 to the power of 0, that equals 1. Essentially, you can think of it as meaning 15 divided by itself. All right, final row, leading us to grade 10 work with exponents. Negative exponents. Should go to this one. What does a negative exponent mean? Well, in its most simplistic, I think, a positive exponent means repeated multiplication. So a negative exponent means repeated division. So x to the negative a means you're dividing by x a number of times. So it's 1 divided by x, whatever a is. So again, if we have like 2 to the negative 3, well, maybe I'll go back to this. If we have 2 to the positive 3, you can think of that, if you want, as 2 times 2 times 2. And if you want, you can put a 1 in the front. 1's like our coefficient. It doesn't make a difference in this case. If we have 2 to the negative 3, you can think of it as 1 divided by 2. Well, that's a weird looking 2. 1 divided by 2 divided by 2 divided by 2. And dividing by 2 3 times is the same as dividing by 2 to the power of 3. And in practice, when we have negative exponents, if we want, we can write them as a positive exponent, but in the denominator. And the other way around, if we have a positive exponent in the denominator, if we want, we can write it as a negative exponent in the numerator. Because again, if I want, I can make this look like a fraction. And chances are in grade 10, you struggled with this at times. Although again, I don't want us to lose sight of the most pleasant part. Positive exponents mean repeated multiplication. Negative exponents mean repeated division. It makes sense. Multiplication and division are inverses of one another. And again, negative numbers are opposite to positive numbers. All right, so what if you have a negative exponent in the denominator? Well, that's the same as a positive exponent in the numerator, so just x to the power of a. And again, I could say over 1. Doing something like that makes the reciprocal aspect of these things look more clear, but really I don't need that. And again, if this was a grade 10 course, I'd go into this more detail, but it's not a grade 10 course, so I'm just reviewing these things quickly. And so when we have a mix, like if we have x to the power of negative 2 over y to the power of negative 3, x to the power of negative 2, I can write as x to the power of positive 2 in the denominator, and y to the negative 3, I can write as y to the power of positive 3 in the numerator. And in practice, when we deal with negative exponents, we tend to see lots of things kind of flipping around because quite often it's easier to deal with positive exponents than negative exponents. All right, and I think that's the last one. Yeah, last one. What if we have a fraction raised to some negative exponent? Well, I could write this, I could imagine the x and the y being raised to the power of negative a. So one thing I could do is write this as x to the negative a over y to the negative a. That said, notice I have two different expressions here, one in the numerator, one in the denominator, that are both being raised to a negative power. So if I want, I can write this with positive exponents. X to the negative a in the numerator is equivalent to x to the positive a in the denominator, and y to the negative a in the denominator, equivalent to y to the positive a here. And again, pretty much identical to what I was kind of reviewing just here a moment ago. And now notice, if you look right here, how similar this is to what we have right here. And so if I kind of take this backwards, I can also write this last expression in yet another way. And I can write this as y over a to the positive a. And so everything here is equivalent. And there's lots of nice symmetry here, especially if we compare the first expression to the last expression. In essence, if we have a fraction being raised to some power, if we change the sign, we just have the reciprocal inside. And so, for example, again, because this is the last one, if I have, a fraction like 2 over 3 to the 4, power of 4, if I want, I can write that as 3 over 2 to the negative 4. Or if I have 1 over 7 to the negative 6, I can write that as 7 over 1 to the positive 6. They're all equivalent. Okay, and that's the key when we're dealing with exponents, especially when we open our minds to negative exponents. There are a lot of different options. Okay, with that said though, in terms of review, and honestly, most of this there's actually more you learned about in grade 10 than just this, but I'm going to stop here because for the first lesson, that's all we need. Okay, and hopefully again, all of this sounds familiar. This is meant to just kind of refresh our memory.